Welcome everybody to the final talk of this semester, right? It's great to see all of you again. It's my great pleasure to have today Dan Král, who will talk about, right, and I will not introduce Dan because you can read his biography. We always do it on the announcement of the seminar. So you can read about great things Dan did, and you can look on amazing list of his papers, which he has on his website. He will talk about uniform Turán density of hypergraphs. Please, Dan.
Yeah, thank you, Benny, for the introduction and also for the invitation to give this seminar. I must say that I am somewhat nervous because this talk significantly goes better with the blackboard or whiteboard than with the slides. So I decided to reuse my knowledge from the COVID times and to use the technology that I used for teaching. So hopefully things go well. And but I must admit that I'm a little bit nervous because I haven't been using this technology for a while. So the topic of today's talk is uniform Turán density of hypergraphs, which is a topic that I have been working on for several years with some breaks. I will mention some old results that we have, and similarly, I will mention some new results. Quite a lot of them is either still to be written up or is a work in progress, but I will get to this towards the end of the talk. So I want to start with recalling some very classical and old results in graph theory, which I assume that everybody knows. Before that, I want also to mention that feel free to interrupt me at any time. I'm not going to follow the chat, but if you have a question, just press unmute yourself and ask the question, and I will be very happy to answer it on the spot.
Yeah, and I also will follow chat, Dan. If I see something, I'll read it to you.
Yeah. Perfect. So the first result that I want to mention is the theorem of Mantel, which arguably might be the oldest result in extremal graph theory, which according to my notes is from 1907, and this is a theorem which concerns the number of edges in triangle-free graphs. So the theorem says that and I'm also trying to do my best with my handwriting. In case it becomes ineligible, please just interrupt me and I try to improve it as much as I could. So every n-vertex graph without a triangle has at most the floor of n over 2 times the ceiling of n over 2 edges. And this bound is tight because, as we know, the extreme example is just the complete bipartite graph with the parts of exactly the sizes. So one can also say that the sizes which are equal sizes may be with difference 1 in case the parity doesn't work. And this result has been generalized in various ways. Perhaps one of the first and simplest generalization is a theorem of Turán from 1941, which concerns the number of edges in a graph and doesn't contain a complete graph of a specific order. So every n-vertex graph without kk has at most, and now please don't torture me with writing the formula, but I just will draw the picture. And the picture is that I will split the vertices of a graph into k-1 parts, which are of as equal sizes as possible, and I put all the edges between. And the further generalization is due to Erdős, Stone, and Simonovic, which concerns the maximum number of edges in a graph that does not contain an arbitrary graph, where when we have the asymptotic result. So let me maybe state the theorem. Simonovic, 1946. And what the theorem states is concerns the number of edges in a graph that avoids a particular graph as a subgraph. So if I'm looking at the maximum number of edges in an n-vertex graph, avoiding G as a subgraph is at most the chromatic number of G minus 2 divided by chromatic number of G minus 1 plus little o 1. And of course, the maximum number of edges is n choose 2. So when I'm looking at it, I think I still have a space for improvement in regard to my font, and I will try to improve it somewhat. So these are very classical results, and they actually lead to the definition of the Turán density of a graph, and more generally of a hypergraph or some other combinatorial structure, which is the infimum over all the densities that do guarantee the existence of a structure. So maybe let me give the definition. Turán density of H is the infimum, and there might be various definitions which are equivalent, so I will just give one. If you have seen a slightly different one, I mean, it should be easy to see, but it's equivalent to the one I'm giving. So it's the infimum over all D, and I have intentionally didn't say whether H is a graph of a hypergraph. In this talk, I will be mostly concerned with hypergraph, but of course, so far I have only talked about graphs. So think of H both as a graph or a hypergraph. Is the infimum over all D such that there exists n0, that for every G with at least n0 vertices, I think I put here a little bit too many every. Okay. Every G with at least n0 vertices and density at least D contains H, where the density is the number of edges divided by the maximum possible number of edges. So in the case of graph, if I have an n-vertex graph, is the number of edges divided by n choose 2. In case of free uniform hypergraphs, so hypergraphs where every edge has size 3, it's the number of edges divided by n choose 3 and so on. So for me, the density is the number of edges divided in case I'm working with k-uniform hypergraph with n choose k, where n is the number of edges. And the results that I have so far mentioned say that the Turán density of the triangle, so for the triangle, the Turán density is 1/2. For the complete graph on k vertices, the Turán density is k minus 2, k minus 1. And more generally, the Erdős-Simonovich theorem says that the Turán density of a graph is fully determined by its chromatic number. The situation is much more complex or much less clear for hypergraphs, and even supposedly one of the simplest cases for hypergraphs, which is the case of the tetrahedron, the complete free uniform hypergraph on 4 vertices, has remained open for many decades. I believe the problem might have been traced to the 50s. So let me maybe state this problem as a conjecture. So it's a Turán tetrahedron problem. And it asks for determining what is the Turán density of the free uniform free uniform complete hypergraph on 4 vertices. So this is, I just draw it in the best possible way I can draw a free uniform hypergraph. So, and there's an extremal construction conjectured. And let me draw a picture. So the extremal construction, which is conjectured to be optimal, is the following. One would split the vertices into 3 equal parts, and there will be 2 types of edges. One type of edges will take 1 vertex from each of the parts. So this will be 1 type of edges. And the other type of edges, so one would think of the parts to be cyclically ordered, and one would take 2 vertices, and I think I should change. I should have used a different color. One would take 3 vertices from one part and 1 vertex from the next part. So this will be. So one can check that the density of this hypergraph is the density of this hypergraph is 5/9, and it's actually conjectured that this construction is optimal for this problem. So the conjecture is that the Turán density of the free uniform free uniform complete hypergraph on 4 vertices is indeed 5/9, and there has been some flag algebra calculations actually showing the upper bound of something like 0.56. So we pretty close to it, but there's no proof of this result. So the reason I mentioned these examples is that if one looks at all of them, they actually have one thing in common. They all of them do contain large independent sets. So each of them has a large set of vertices with no edges at all. Okay. So the ones that I'm now highlighting in orange. And the question is whether anything changes if one imposes an additional constraint that the host hypergraph or the host graph does not contain a large set with substantially lower density than is the overall density of the hypergraph. So this question goes back to Erdős and Sós in the 80s. And brings us to the definition of the uniform Turán density of a graph. So this notion goes to the 80s, to Erdős and Sós, who specifically ask, and I will give a definition in a second, about the uniform Turán density, define uniform Turán density in a second, of the tetrahedron, and also of the so-called broken tetrahedron, which is the tetrahedron with 1 edge removed. This is, I have 4 vertices, but I have only 3 edges. So what is the definition? So the uniform Turán density. And we have several equivalent definitions. Again, I will try to give the one which I personally find the easiest to digest, but of course this is a matter of personal preference. But the idea is that now we want to look at the minimum possible density which forces the presence of a hypergraph H with the additional constraint that there's no sparse part of the host hypergraph. So the uniform Turán density of, and I would normally write K uniform hypergraph, but let me just write K graph. So now I mean the K uniform hypergraph, so the hypergraph where every edge has size K. K graph H is the infimum over all these, such that for every positive epsilon where exists and 0, such that every K graph G with n larger than n0 vertices. And now there will be a condition which constrains that the number of edges is uniformly spread. So for every A subset of the vertices of G, the size of A is at least epsilon times n. So I'm saying that for an arbitrary small but linear size set of vertices, the number of edges of G restricted to K is at least D times the maximum possible number of edges. And this implies this whole condition. This implies that H is a subgraph of G. So maybe I should have drawn this slightly different. Wait a minute. Maybe I should have circled this. So this constraint is clearly the variant of the Turán density. So in the Turán density, I'm constraining the global density. I'm saying that my host hypergraph has a certain number of edges, and I'm hoping to find a copy of H. In the uniform setting, I'm saying that every linear sized part, and there's a certain interplay, what I mean by that, has a density D. And when I'm asking whether when I'm hoping or I'm looking for the minimum possible D or the infimum among all these that guarantee me the existence of a hypergraph H in the host hypergraph. So I do realize that this is maybe, I mean, I would say this is the most technical definition and maybe even the technical part of the talk. I think the rest will be significantly easier, but it will be quite important to follow the next 25 minutes or 35 minutes of the talk. So maybe I should pause here, and if there are any questions, then just take them at this point.
So done. So basically, kind of it requires some lower density even on small subsets of linear size, right?
Correct. Correct. So there is actually a very, since there are no further question, I will continue. So there's a very striking difference between the world of graphs and hypergraphs. So the motivation for this definition was that all the extremal construction or for the Turán problems, they usually come with large independent sets, like the set of size 1/2 in the case of the triangle, the sets of sizes 1/k-1 in the case of the complete k-partite graph or more generally k-chromatic graphs. Also in the conjecture extremal construction for the Turán tetrahedron problem, we see independent sets of size 1/3. And this condition forbids not only like a constant size, but any linear size independent sets. So I will keep the definition. I will keep for the time being also the definition of the Turán density. And this. And we'll try to say a few basic facts. So the first fact is that the notion of uniform Turán density is very boring for graphs, because the uniform Turán density of any graph is 0. So it's not a hard exercise. This can actually be maybe even given as an exercise for once one introduces the regularity lemma, and it's rather easy to show that in the case of graphs, the situation is very boring. The uniform Turán density of any graph is simply 0. However, the situation becomes much more interesting in the case of hypergraphs, and unfortunately, also the case of the tetrahedron, similarly to the usual Turán density, has been open now for 40 years. But there's a conjecture. So the tetrahedron So for the K4 free, the usual Turán density is conjectured to be 5/9, question mark. The uniform Turán density, and I will show a construction in a second, is conjectured to be 1/2. So the problem of determining the uniform Turán density goes back to Erdős and Sós, but I do believe that the construction that now I'm going to present is a construction due to random. So what I need to do, I need to construct a large hypergraph. So I want to now to show the lower bound. So what I will be doing is I will be showing the lower bound. So I will be constructing a large hypergraph where every linear size subset of vertices has density half minus epsilon or minus delta, but I don't overuse the epsilon. So what I'm going to do, I will take vertices, I will take n vertices and order them linearly. And now I will be coloring their pairs randomly with two colors. So I will be using, let's say, red and blue. So for every pair of vertices, I will randomly flip a coin independently of all the other pairs and color it either red or blue. So I will not clearly color all the pairs. I just wanted to hint what's happening. And now a triple of vertices. So if I look at three vertices, I should have drawn it slightly differently. If I look at three vertices, so maybe I look at these three vertices. So this triple of vertices will form an edge if the colors of the pairs involving the leftmost vertex are different. So it will form an edge if one of the pairs is red and the other one is blue. So this is an edge. This is an edge. So these are edges. But if the colors are the same, so for example, they both blue, when it's not an edge. Yeah, so I will include a triple as an edge if the colors of the pairs involving the leftmost vertex are different. So clearly the probability that a particle triple is an edge is 1/2. And it's easy to use like standard estimates on martingales to show that every linear size subset of the density of every linear size subset of vertices, the number of triples it contains as edges is at least half minus delta. So basically there's a concentration. I cannot go with the usual Chernow because I have dependencies, but it's not hard to use martingales estimates just to show that indeed the uniform density of this hypergraph is half minus delta with high probability. And this hypergraph does not contain the tetrahedron. And the reason is very simple, because if I look at any four vertices and I look at the pairs involving the leftmost vertex, because I have only two colors, there will be two pairs with the same color. So maybe this pair and this pair has the same color. But when these triple vertices cannot form an edge because the pairs involving the leftmost vertex have different colors. It's somewhat funny that in this argument, I actually never constrain the edge involving the second, third, and fourth vertex. So basically the argument actually excludes the presence of the tetrahedron in somewhat stronger sense. But this is the best construction we have, and it's actually conjectured to be the optimal construction. So I should maybe pause here again. So what I have so far shown is I have given the definition, and I have shown that in where we believe that the uniform Turán densities in principle may be lower, and for graph the situation is boring. So it makes sense to look at the free uniform hypergraphs, and I have given an example of a free uniform hypergraph with the uniform Turán density close to 1/2, which does not contain the tetrahedron, linking or kind of giving some evidence for this problem on determining the uniform Turán density of the complete free uniform hypergraph on four vertices. So I will now erase the definition of the uniform Turán density and start mentioning some already somewhat old results, not super old, but somewhat old results on the uniform Turán densities of hypergraphs. Of course, if there are any questions, I'm very happy to take them at any point. So there hasn't been too much progress on the uniform Turán densities until about 10 years ago. And as I mentioned, Erdős and Sós specifically asked about determining uniform Turán densities of two graphs. One of them is the tetrahedron, which is still open. The other one is the broken tetrahedron, which has been resolved. So we have a theorem. Let me actually change the color. And it's a theorem due to Roman Glebov, myself, and Honza Volec from 2016. And what we have shown is, that the uniform Turán density of K43 minus the broken tetrahedron, which is the other hypergraph that the Erdős and Sós specifically asked about, is 1/4. So we have used the flag algebra method for our proof. So this proof is based on flag algebras. These are the computer. This is a computer-assisted method for proving asymptotically true inequalities due to Rasborov. But the good news is that we now actually have a completely, I don't know whether human is the right adjective, but now we have a completely human checkable proof, which is using hypergraph regularity. So the result was proven using hypergraph regularity. By Christian Reyer, Vojta Redl, and Matthias Schacht in 2018. And since then, I should mention that all the other results that I will be presenting or mentioning in this talk were actually based on the hypergraph regularity. So there's no more flag algebra results. So we have proofs that we can actually see what's happening with the host hypergraph. So at some point, I should give a little bit of hint how the hypergraph regularity is used, but let me not do it for this result. Let me mention another result, also due to Christian, Vojta, and Matthias, where I would maybe give a little bit of hint how the hypergraph regularity may be used. I don't want to go into extremely technical details. I just want to give a hint how it comes into the play, and then maybe like hint how further results in the area do actually extend the ideas that appear in that papers. At this point, I should also mention that in case you would like to follow, there's an excellent survey. There's also a survey by Christian Reyer, which is maybe about 5 years old. So some of the newer results are not reflected where some of the problems from the survey has been meantime resolved, but it also gives the hypergraph regularity method as a kind of nice, like a toolbox that one can maybe, when working in this area, avoid some of the most technical arguments and go directly to exploiting what the hypergraph regularity gives as the power. So as I said, I'm very happy to take questions at any point. But I want to mention another result, which actually somewhat started another theme, which is somewhat similar to jumps for the usual Turán densities of hypergraphs. And it's a theorem, again, due to Christian, Vojta, and Matthias. Again from 2018, but it's a different paper. And what they have shown is that the uniform Turán density of a free uniform hypergraph, so let me again just write free graph H, is either equal to 0 or is at least 1/27. So they show that a jump that there's no pre-uniform hypergraphs of uniform Turán density between 0 and 1/27, and they have even given a characterization of those hypergraphs of uniform Turán density 0. So let me give that characterization. So the free uniform hypergraph H has uniform Turán density 0 if and only if H is a subgraph or of the. So let me maybe do it semi-constructively, and it will be obvious where this 1/27 comes from. So if and only if H is a subgraph of sufficiently large hypergraph, which is obtained in the following way. One again takes the vertices, order them from left to right. And this time I will be coloring their pairs with 3 colors, red, green, and blue. So I will randomly color the pairs of vertices with 3 colors, red, green, and blue. And I will include a triple as an edge, if and only if it looks like the triple I have just shown. Maybe I use slightly different green when it's more visible. So the left and the middle vertex form a red pair, the middle and the right vertex form the green pair, the left and the right vertex form a blue pair. So this is an edge, and any other triple is not an edge. So if H is a subgraph of sufficiently large hypergraph of this form, when its uniform Turán density is 0, this can of course be equivalently formulated that I can order the vertices of H and color their pairs with red, green, and blue, such that all the edges of H actually look like this allowed triple. And if it's not a subgraph of any sufficiently large hypergraph like this, then this is actually a construction, again, like just using the usual concentration of a hypergraph with uniform Turán density 1/27. So it must have uniform Turán density at least 1/27. So what I do believe that I have shown is that if H is not a subgraph of any sufficiently large hypergraph of this form, like let's say random hypergraph, where the randomness comes from choosing the pairs of vertices, its uniform Turán density is at least 1/27. What I now will hint is that if H is a subgraph of any such sufficiently large hypergraph, so equivalently, the vertices of H can be ordered and where pairs can be colored with red, green, and blue. Let me try to do my best to do an as most illustrative example as possible. Such that every triple, so let's say this is an edge, this is another edge, but every edge is kind of consistently colored, pairs consistently colored, when I claim it has uniform Turán density 0. And let me just maybe briefly hint why this is the case. So basically now I believe that I will now lose like 90% of the audience, but I hope that this will only happen for 2 minutes. So I just want to give a hint how the hypergraph regularity comes. So if I have a large host hypergraph with positive density, I apply the hypergraph regularity lemma. When using standard Ramsey arguments and using the uniformity, I will just obtain a large part of this regularity decomposition where every triple has positive density. So basically, I will have parts where every triple has positive density. So if I take any 3 of them. And what the hypergraph regularity lemma permits, it permits me to split the auxiliary or the non-existent complete bipartite graph between parts into quasi-random bipartite graphs, which actually drive the density of the hyper edges. So for every pair of parts, I have a partition into many quasi-random bipartite graphs. And now what I will do, I will choose one of these, and that requires a tiny argument. One will choose one of these bipartite graphs to be kind of red. One will choose one of them to be blue, and one of them to be green. And maybe prune this part of the partition to a smaller one in such a way that whenever I will take 3 parts, from let's say left to right, and I will look at this red bipartite graph, at this green bipartite graph, and the blue bipartite graph, when actually the triad waveform will have a positive density. And when this will allow me to embed H into this part of the regularity decomposition, and therefore I have found it. So I do apologize for those who are not particularly familiar with the hypergraph regularity, but I just wanted to give a hint how it comes here. And this was a very easy application. And the additional results that I will mention in the talk, they actually use the same idea, except the number of colors or the number of these auxiliary bipartite graphs. One needs to get a significantly bigger control. They're usually more when there's several outcomes saying, okay, one can get this outcome, this outcome, this outcome. And then for each of the outcomes, one needs to find H as a subgraph. So I'm quite oversimplifying, but I don't want to get too much technical, but I still wanted to at least hint the ideas which might be coming behind them.
I have one question about this. I'm not sure if you will talk about it, but is a similar result true for higher uniformities as well? Say,
yeah,
for
excellent question. So the question, so for the higher uniformity, it's known there will be a gap, but it's not known how big the gap will be. So what is open is to determine what this value 1/27 is. And actually, that's something I wanted to mention. Notice that what Vojta, Christian, and Matthias proved, they actually proved a gap, but they didn't show that the gap is 1/27. They only showed that the gap is at least going to 1/27. And I should actually mention, and that's one of the results I wanted to mention, that together with Frederik Garbe and under Lamaison, the paper has been accepted to Israel Journal, but not published yet. We have shown that there exists a free graph with uniform Turán density 1/27. Actually, so we have actually shown that this 1/27 is the right number. For higher uniformities, it's not super hard to show that there will be a gap. What is hard to show, what is open, is what the gap is, the exact value. Thank you for the question.
So Dan, so in this case, so in the case of usual Turán densities, there is this very natural thing like partite hypergraph, complete partite hypergraph, which gives you a separation, right? If you can embed there is a Turán density 0, and otherwise it jumps because you already, right? But so here there is no natural thing which you would believe, or no. I mean, one thing is proving, but at least there is a natural sequence of examples.
I'm not sure I completely understood the question. Oh, so you're asking about this 1/27?
Right. If there is a natural sequence of examples, right?
Yeah, so we actually constructed several of them. So basically what we did is that we constructed, we actually, first of all, prove a necessary and sufficient condition for a hypergraph to have a density 1/27, which was done through kind of showing that once the uniform density of a hypergraph crosses 1/27, when some configurations might appear, and the configurations are somewhat natural. So what one would expect is that one of these, so basically, so let me try to say the intuition behind. I'm not sure if I will succeed, but I do my best. So the intuition is that somehow when one crosses the density 1/27, when it won't be anymore possible to kind of say in the hypergraph regularity that I have some hypergraphs that only appear in these dense triads in the left middle pair, some in the middle right pair, and some in the left right pair. So basically what I will need to have, I will need to start having some overlaps. So for example, an overlap with one of the colors. So maybe now let's say red color will appear in some of the triples as the middle right color, and in some of the triples as left middle color. So basically there's kind of an intuition that this what happens at 1/27. One can formalize it using the hypergraph regularity, therefore gets a necessary and sufficient condition on the hypergraph, and then just needs to construct a family of hypergraphs, or at least one hypergraph, but we actually had a family satisfying these conditions. I don't know whether I answered the question, but
yeah, no, I understand. It's getting complicated. Yeah, I understand. No, what I meant to say is that for usual Turán problems for hypergraphs, right, the solution is very simple, right? You either if your Turán density positive, it's immediately bigger than the density of complete partite hypergraph which you can find. But here it's a kind of a constructions getting extremely kind of sophisticated, right?
yeah, so both the lower bound construction and also like and actually what's even getting harder is to do the upper bounds, because basically one needs to inspect the hypergraph regularity partition and see what kind of overlaps between these quasi-random bipartite graphs one gets, and basically extract information from that.
I see. Mm-hmm. No. Okay.
So I still have 10 minutes, which I was hoping I would have more time at this point, but so I will at least try to formulate some of the results we have proven, and some very recent results. So one of the questions, so I want to mention the following two theorems. So one is a little bit older and it's actually related to ETH, where it was proven during my stay at ETH, and involves a couple of I believe at this point current and former students of Benny. So it concerns a question, one of the questions which was mentioned actually in the Christian survey I gave as a reference, and it concerns the uniform Turán density of tight cycles. So this is a result joined with Matija, with J. Cooper, Samuel Mohr, and David Munhá, Correia. And the paper was published actually last year. And it concerns the uniform Turán density of a tight cycle. So cycle C. Okay. So what do I mean by a tight cycle? I just take vertices. And when any cyclic triple of them forms an edge. Okay, let me just and what we have proven, so this is I mentioned this was posed as an open problem in Christian survey. We have proven that the uniform Turán density of this cycle is 4/27 if L is not divisible by 3 and L is at least 5, and 0 if L is divisible by 3. So if L is divisible by 3, this is very easy because one just goes to this theorem by Christian, Vojta, and Matija. What was hard was to show this 4/27. And I should mention, just to give a glimpse of complexity. So basically, in order to prove this result of Christian, Vojta, and Matija, one essentially gets only one kind of configuration from the hypergraph regularity. In order to prove this result, one gets 2, but in our result, we had about like 16 possible configurations coming out. So basically, we kept analyzing the hypergraph regularity decompositions, getting different outcomes, and based on non-existence of the outcomes we have ruled out earlier, and based on the assumption on the uniform Turán density, we always found a tight cycle, get another configuration, excluded it, and so on. So until recently, this was pretty much the state of the art, in the sense that these were all the hypergraphs for which we knew the uniform Turán density. And were various questions. So first of all, we have seen a jump. So another question might be whether 1/27 is a jump. And I don't know the answer to that, but I do suspect it may be a jump. But what I do now know is that it's not a jump all the way to 4/27. So it's a very recent work in progress. Together with my student Filip Kučerák and Gábor Tardos, we actually constructed a hypergraph with uniform Turán density 4/81. And I personally do actually believe that there's a jump from 1/27 going to 4/81, but we're not able to prove that, and that's actually part of this work in progress, because that, of course, what we're trying to shoot for. And there's a slightly older work that we somewhat not very efficient with writing up, but that's actually not a work in progress. That's a theorem, and I would like to maybe spend the last 5 minutes just giving some hints how the theorem is proven. And it's a joint work with Frederik Garbe, Daniel Iľkovič, Filip Kučerák, and under Lamaison. So I will put here 24 with 2 pluses. I'm kind of hoping the paper will appear on arXiv in the next couple of months. And it's actually been written up. It's one can find the complete proof in the bachelor thesis of Filip. And so the proof is in the written form, but we still haven't yet prepared the paper. And what we did is we constructed a uniform hypergraph, and I will say a few words about the construction. Hypergraph. With uniform Turán density 8/27. So just to recall what numbers we know, we actually know very few numbers for which we have a construction of a hypergraph. So it's known 0, 1/27, 4/81, 4/27, and 8/27. So these are the only values for which we know a construction of a hypergraph. So let me maybe give you the construction of this hypergraph, because I think it's actually quite a nice construction.
Dan, wasn't 1/4 another number you knew?
Oh yeah, quarter, you're right. The very first one, thank you. I knew that I will forget one. Thank you, Yuval. Yes, of course. And where does it go? Here it goes. Thank you. So the construction goes as follows. So one takes a large set of vertices. And covers it with 5 tuples, such that no 2 5-tuples overlap in more than one vertex. So basically, one can think of it as a design. We have now this super powerful results when we can do it perfectly, but for me, it would be enough to do it almost perfectly. So I also like where some finite constructions known. So basically, what I just need to have, I need to have a large set of vertices where I have a collection of 5 tuples, such that no 2 of them intersect more in one vertex. And what I need to know is that the number of these 5 tuples is roughly n choose 2 divided by 10 minus little over 1 squared. And what I can achieve for some n's, I can do it perfectly. And actually, n, which is quite small, suffice for the construction, but I want to present the construction in functionality. And now what I'm going to do, for every 5 tuple, I will randomly pick 2 vertices. So in each 5 tuple, I will randomly pick 2 vertices. So let me call them x and y. The remaining vertices are alpha, beta, gamma. And now the hyper edges, or the edges in my hypergraph, will be xy alpha, xy beta, and xy gamma. So this is the construction. So this so it can be shown that the uniform Turán density of this hypergraph is that I can find this hypergraph in any hypergraph if the density at least 8/27, but requires, that's actually not like super easy, but it's also not like something that would be spanning more than, let's say, 10 to 15 pages. But let me actually show that with, so this was a random construction. So let me show that with high probability, the uniform Turán density is at least 8/27. And I will, again, it will be a coloring construction. And there will be 3 colors. So there will be red, there will be green, and there will be blue. And the following triples will be edges. So there will be in total 8 triples. And I want the first color not to be red. So let me maybe, and I realize that I'm slightly running out of time, and this is the last proof that I want to present. So I want this pair not to be red, this pair not to be green, and this pair not to be blue. So again, like this is a construction with the density 8/27. And why this hypergraph does not appear in this construction? So if I take a random ordering on these vertices, what cannot happen in that ordering, what is bad in that ordering is, if in that particular ordering, and I have n factorial of such orderings, the vertices x and y appear on this position. Yeah, so if I take an ordering of these vertices, of the vertices of this hypergraph, if x and y appears on this position, I definitely cannot find this hypergraph with that ordering in this construction. So I have n factorial orderings. For each of the 5 tuples, I have 9 possibilities are good, 10 are bad. And when one just basically looks at this number and see that with high probability, I will find. So I know I ran out of time. I maybe didn't completely spell out the argument here. And I will just stop. Yeah. Thank you for your attention. And I'm happy to take further questions.
So thank you, Dan, for a very interesting talk, right? So maybe let's give Dan a round of applause. Yes, so was nice to see all these ideas and proofs. So any questions, please?
So I'm curious, so it seems that all the constructions you know are of the form like color the edges in some finite way and then define the hyper edges by some allowed or disallowed configurations. Do you believe that these are the only constructions, or that somehow this is the best you can do?
And I was thinking whether I should mention it as an open problem, and I intentionally didn't want to mention it as an open problem, even if this appears as an open problem in Christian's survey, because I actually got an email from under Lamaison a couple of days ago, and he believes that he can prove it, but he doesn't want to claim it as a result. So I was asking whether like it's a claimable result. It's a work in progress, clearly. So, you know, so I kind of wanted to be walking around it, but it was obvious that somebody would ask. So I actually do believe it's true. And there's some work in progress, which might be a claimable work in the order of a week or two due to under, you know, as I'm saying, I specifically asked him whether I can announce it as a result, and he told me that he still wants to verify the proof before it is claimed, so it's not yet a result to be claimed.
Okay. Yeah, thank you.
But just wanted to ask, but some of this construction also can be said in the language of tournament and orienting the edges, and then
that's correct. But
and this is exactly equivalent with the coloring.
Absolutely. So the constructions you talking about is actually for the broken tetrahedron, and basically the construction goes as follows. So one will take vertices and orient every pair. So basically take a random tournament. And then an edge will be cyclically oriented triangle. So this is an edge. And it can be shown that this construction gives density 1/4. No, because if I take a randomly oriented pairs with probability quarter, I will see a cyclic triangle. And it doesn't contain a broken tetrahedron because, so without loss of generality, this is my first triple. When this uniquely determines the orientation of the pairs involving this triple, and I clearly don't see anything else. And this construction indeed can be cast in the coloring, because I will order the vertices, and if a triple is oriented this way, I will just color it red. If the triple is oriented the other way, I will color it, let's say, blue. And when the edges are those triples that look either like this or like this.
Mm-hmm.
So in this was an easy reduction. Even for this problem, the construction with the orientation is maybe easier to explain. It's much easier to see when the broken tetrahedron doesn't exist, but there's an equivalent coloring construction.
I see. Okay. More questions? If
Actually, I have,
yeah.
sorry, I have one more question. So if you believe that if this result of under is correct, then somehow does that mean that at least in principle, any such Turán density you could prove using hypergraph regularity? Like somehow you would need to analyze some finite list of configurations, but like there is sort of for any given H, there is some finite list that you would need to understand.
That's not clear to me because I don't see, so Wedgwood means I just need to analyze this, let's say, coloring scheme constructions. But what I don't see is an a priori an upper bound on the number of colors just in terms of the hypergraph. Because I can imagine there might be some very weird lot of colors which somehow strangely interact. I don't see this. So I don't see the problem becomes a priori finite. It becomes definitely easier. So for example, in that results with Matija that I mentioned, we knew that by coloring constructions, one cannot go below 4/27 for quite a long time. And what was hard was actually to get it through the hypergraph machinery. So the problem definitely becomes easier, but I don't see like it becomes finite.
Okay.
But it can be true such theorem because it's like would be really cool, right? Like a forbidden minor theorems like for this type of thing. So you say that every time there is a finite bound which you need to check, maybe extremely huge. Is it potentially might be true, or you think that?
I would think I would be extremely surprised if there would be a hypergraph for which one actually needs to do like kind of infimum or the supremum of these coloring constructions. But I would not be surprised if there would be a family. Maybe some nice family, but one specific hypergraph, I would be somewhat surprised. But it's just an intuition.
Thank you. More questions? If not, let's thank Dan again, right, for a beautiful talk. We can stop recording.